What's going on, everyone? It's Jaren from Jarenism.
Yeah, so this week, Jaren from Jarenism has been giving us his wisdom on the fact that we have a gas pressure on Earth next to the vacuum of space. Here's what he thinks of it.
Yes, another runner-up in the growing list of pseudoscience that's taught to us as actual science.
So originally I was going to put this video on the Conspiracy Catz channel, not the Baldy Catz channel. I even put a poll out on my channel to see where it would fit best. And although a lot of people did say, put it on the Conspiracy Catz channel, there was enough there that made me think the Baldy Catz channel is the right place. And that's because it's difficult to make this video with silly bits of editing like this. And still make it mature enough to get the point across that I want to make. Now, at the minute, there are so many flat earthers on the internet who are clinging on to this gas pressure of the Earth's atmosphere next to space. And they do it because they see idiotic, intellectually dishonest videos like this one.
So there should be no reason why you couldn't put a gas pressure in there, put the lid on it, pull the lid off once you've got the pressure, and because of gravity it would hold the pressure in there. Wouldn't it? That's what it would literally do according to your model.
And this one.
What I would like you globies to do is to contain air pressure without a container. Dead easy.
By the way, Ranty, how confident are you that the Earth isn't round?
49%.
I thought you'd be more confident than that. And of course, we've got this idiot.
Welcome to an idiot's guide to gas pressure. No whiteboard required.
Oh.
This contains pressure. This is a lower pressure system.
Yeah, so this is Nathan Oakley, the guy who's famous for not being able to convert kilometres to metres and for openly admitting he has no idea how a solar eclipse is formed. But that's not going to stop him giving us a lesson on the second law of thermodynamics and entropy. Dunning-Kruger at its finest.
Oh, it seems to have disappeared and we're only left with the container. Entropy's a bitch if you believe in the heliocentric version of space.
Alright, let's lay this out in a few diagrams to explain it.
Right, so now Jaren from Jarenism is going to use his childlike understanding of science to explain to us exactly what the problem is. I just hope he gets his diagrams right.
So, in the first diagram we have a container, and we've got gas pressure, or air.
Yeah, I thought he'd struggle. I'll do the diagrams. So this is what he's starting with.
And then we've got a divider, and then we create a vacuum in the right side of the container.
Yeah, like this. Now, he's got some professional help with the rest of his diagrams, so hopefully I can put this away for a bit.
Okay, now here's the problem for globe defenders and space religious zealots. If I lower the divider just a tiny bit, just bring it down a hair, what do you think will happen to the gas on the left?
I think what will happen to the gas is exactly what the heliocentric model predicts will happen to the gas.
The gas will dissipate and fill the entire void. High pressure to low pressure, always.
Brilliant. So why is this a problem, Jaren?
There's the Earth, and on it we have gas pressure. But there's no container. It is simply pressing down. But above that is the endless, expanding, empty, extremely low pressure of outer space without any divider and without a container. Well, that's simply insane and impossible.
Jaren, if you think like a 5-year-old, you get confused like a 5-year-old. Now let me make it very clear why I'm making this video today. I'm making this video because originally I was going to hold this point back so I could use it in a debate against Nathan Oakley, perhaps on the Non Sequitur show, something for charity. But we all know that if Nathan's not making money out of it, he's not going to do it. I've offered Sleeping Warrior, I've offered Ranty, I've offered to pay £200 to the charities of their choices, and all of them have declined. And it's becoming increasingly apparent to me that none of these people believe that the Earth is flat. They are in it for one reason only, and that is to build the YouTube channels to make as much money as they possibly can. They are not interested whatsoever. I have zero respect for any of the Flat Earth debate team left. It's just become an absolute farce. But the question that they're putting out there, entropy is a difficult subject, right? So let's have a look at how we reply to that question and why does it not defy the laws of entropy. So this is really for you guys, not for those Muppets. So let's begin. Okay, so anybody who knows anything about entropy and thermodynamics knows that this can't be done justice in, a 15-minute little discussion. These are the points that I'm going to tackle. What I would love is an intelligent response. And I'm not going to get an intelligent response to any of this. Like I said, this is just for you guys. But if I do, you know, if there is a flat earther out there that listens to what I say here and then wants to ask an intelligent question, then I will do follow-ups. For those of you who are out there who are brilliant at, you know, at your science and you want to leave extra stuff in the comment section, brilliant. But I am pitching this at a level where hopefully we can all just get it, and then we've got a reply we can give. Right, it's a big topic. So I'm going to start with what is pressure. So pressure is defined as the force per unit area. So in other words, I have to have a force upon an area, and with gas pressure, this is my living room and these are the particles flying around. Gas pressure occurs when the particles bounce off the walls or bounce off the ceiling and they create a force. Now the force, we can even calculate, it's the rate of change of momentum of each particle. Just throwing that in there for no reason really. But when they bounce off the walls, they create a force, and the force upon the area of that room will give us the pressure. And we know at sea level, the pressure we get is about 14.7 psi. Now, the thing is, and I've asked this to Anthony Riley and the response was laughable. What if I'm talking about this point here, right above my carpet on the living room? What is the pressure at this moment, right there, right now? Well, right now, those particles are not colliding on anything. They may be bumping into each other. Okay, so I'll give you that. They may collide against each other. But what surface are they exerting a force on? It's not until I put an object in that area for those air particles to collide off that I'm going to be able to measure a pressure of 14.7 psi. They need the area to bounce off, to change their momentum against, to create that force, to create that pressure. So this is where the comment, you know, no balloon, no pressure come from, that they obviously take out of context and twist because they're intellectually dishonest and they don't fully understand the concepts and they don't want to understand the concepts. You know, so if I have a balloon here, right, what I was talking about with the whole no balloon, no pressure, I'm talking about the outside of the balloon. If the balloon is there, then the particles are going to strike the outside of the balloon and they're going to cause a pressure of 14.7 psi. You take the balloon away, what surface are they now hitting? They're not. So flat earthers seem to think that somehow the air pushes like a rod, you know, and that fixed sort of structure will push against the ceiling, push against the floor, and unless the air has something to push off, similar to the ridiculous comments about rockets in space, unless the air has something to push off, or unless it's pushing off itself, there can be no pressure pushing outwards. But that of course is absolutely ridiculous. They need to be striking a surface. That's what pressure is. So what is the difference between pressurized and pressure? Well, this is how I'm going to explain it. And again, obviously, it goes much deeper than this. But if I take a gas, that gas is going to spread out and increase its volume at any given temperature. And as I increase the temperature, the gas is going to spread out even more. And if I increase the amount of gas, the amount of particles there, it will spread out even more. Now, we know this, and anyone who studies sort of like molar calculations and with gases, we know that 1 mole of a gas at a given temperature will occupy a certain volume. And if I increase the amount of gas, it's going to occupy a bigger volume. That's just a demonstrable fact, which we can go into in another video, should anybody actually be interested in that discourse. But what if I stop this gas being able to spread out? What if I put it into a container? So here is the gas. Now, this time, as I add more gas, it's not going to make this. It's not going to make the gas increase in its volume. I have fixed the volume. The volume now cannot change. So as I add more gas, what happens is there are more collisions between these gas particles and any surface that's inside. Now that will include the inside of the container, but also anything like a balloon that I might put inside the container. So the pressure per square inch is going to increase as I add more and more and more gas because I've got more frequent collisions. Now this is really what we mean by pressurized. If I take the walls away, then that gas will expand, and it will expand to a given volume dependent on the temperature and the number of moles or the number of particles of gas that I've got. But to pressurize something, you fix the volume. Now, we all will have seen this relationship at some point at school. PV equals nRT. Some people will still be working with this now, but what this essentially tells us is that the pressure times the volume of a gas will equal the temperature times, now I'm not going to get heavy into this, but this basically tells us the number of particles of gas. So if I increase the number of particles of gas and the temperature doesn't change, then the pressure is going to increase if the volume is fixed. So if I'm in a canister or a domed earth, for example, the volume is fixed, so the pressure is going to go up. That gives us this relationship that PV over T equals a constant. All right. Now I can use either one of these formulas, but why is this important? Well, think about the Earth. So basically the Earth does not behave as a container with a fixed volume of gas, because if it did, if the volume was fixed because we had a container over the top, then the amount of gas we also would be fixed. And that would mean that the pressure is directly proportional to the temperature. So as the temperature would double, the pressure would double, but we don't see that relationship. We don't see huge changes in pressure at sea level as the temperature changes. Now, for those a little bit more advanced, we'd have to convert the temperature to Kelvin and not degrees. Again, if anyone's interested in that chat, if a flat earth wants to discuss this, I'll discuss it. Essentially, so gas pressure on Earth just does not behave like pressure in a container behaves. It just doesn't. We do not have this fixed volume capped by a dome. If we did, we would have a fixed volume of gas, and what we would find, like I've said, is if I increase the pressure, I would get I would get a proportional increase in pressure. You show me a container anywhere on Earth, where I can increase the temperature and the gas inside will have varied responses to the response in terms of its pressure. And you won't be able to find one at all, because it doesn't exist. But of course these guys will just completely ignore that. So let's move on to number 3. What is entropy? Good question. Now I could be here a long time with this question, and I'm not going to be. Like I said, if I get sensible questions and requests based on this, I will do more. But essentially all we need to know at this level at the minute is to do with the spreading out. But it's not to do with spreading out of mass. And this is what, again, flat earthers would have you believe. If I have lots of gas particles here, we do know they are going to spread out. But it's not the spreading out of the gas particles that follows entropy. What entropy is the spreading out of energy. If I take these gas particles here and I was to measure the kinetic and potential energies, then I have a lot of energy contained in a small space. When they spread out, they are dissipating that energy with them. They're spreading that energy over a larger area. We talk about order to chaos, all right? And that's essentially what entropy is. So what is the law of entropy? Well, the law of entropy is essentially that the entropy in the universe must always be increasing. In other words, the energy of the universe is spreading out. That's not necessarily the same as saying the matter in the universe is spreading out, but the energy in the universe is spreading out. But that's across the universe. On a local scale, we see the opposite of that many times. But energy on a local level can be decreased. So let's think about a cup of water. And the particles are flying around with all the kinetic and potential energy moving around everywhere. And then I freeze it and I form something where the energy is less spread out, like in an ice cube. Here I am decreasing, I'm making them more ordered, I am decreasing the entropy. Now that's on a local level, but how do I freeze my ice? Well, I put it in a freezer. And inside the freezer, there'll be processes taking place where entropy is increased in order to achieve the cold environment. But we don't need to know how a fridge works. We can go back to the power station that the fridge is plugged into. And there I am burning coal, I'm burning fossil fuels, where I'm increasing the entropy at the power station side to allow me to decrease entropy here. But overall, the entropy will be increasing. So on a local level, a decrease in entropy, we see it all the time. So let's apply that to a number of different ways we can show that the laws of entropy are not being broken by having a gas pressure next to a vacuum. And it's going to be a while before I even say the word gravity. So remember, it's the amount of entropy in the universe that has to increase. So these gas particles here that gain their kinetic energy that allows them to rise up, where do they gain that kinetic energy from? Well, they get heated by the ground. And how does the ground get heated? Well, it gets heated by the sun. And in the sun, we have huge amounts of nuclear fusion taking place and huge amounts of energy being released and spread out through the entire solar system. There is not a bigger source of increase in entropy than the sun. And if that causes these gas particles to gain energy and rise, even if they don't suddenly jump off into the vacuum of space, the sun itself is showing that within the universe, entropy, or within our solar system at least, entropy is being increased. But that's a really basic answer, so let's look a little bit further. So, why can the particles move? Well, the particles can move because they absorb heat energy, which is turned into kinetic energy. They get that from the ground, again, which comes from the sun. And as they rise with their kinetic energy, the temperature of the atmosphere starts to drop. And they radiate off some of that energy. They radiate off that heat energy in all directions, which would be an increase in entropy. And as they radiate out that heat energy in all different directions, they lose kinetic energy and they start to slow down. And because they start to slow down, when they hit something, they don't hit it with as big a force anymore. So the pressure is going to drop because they're not striking with as big a force over that area. The rate of change of momentum for any collision is much, much less. But also, to get that high, we can use what we call the Boltzmann equation. And in the Boltzmann equation, this can be considered a representation of the entropy per molecule. Now, I've used the Boltzmann equation before, and people like Anthony Riley have said, oh, it's just a statistic probability. They don't understand that entropy is actually included really in the Boltzmann equation. But the Boltzmann equation can allow us to accurately predict how many particles will have enough energy left to reach a certain height. And that is what we see. That's represented by what we see in the real world. So I'm just going to take a little break here because this is getting quite heavy and dragging on a bit even for me. But let's revisit what we talked about. The Earth's atmosphere does not behave like it's in a container. If it did, then PV over T would equal a constant. The volume will be fixed, which means P over T equals a constant. So in other words, the temperature would always have a proportional effect on pressure. And we don't see that on Earth. With the difference in temperatures locally and at different altitudes, we do not see that effect on pressure at Earth. It does not behave as if it was in a container. If you're going to try and tell me that there's a dome, you're going to have to show me a container where we do not get a proportional increase in pressure when we change temperature. Good luck with that. You'll never do it and you'll just ignore that point. Secondly, this whole silly entropy argument, we have to start accepting that the law of entropy says that it must be increasing, but across the universe as a whole. And we've talked about how the sun is a huge increase, or a huge source of increased entropy in our solar system. But also, as the particles rise through our atmosphere and they start to cool down, they start to radiate heat, they're adding to that increase in entropy. But what I really should emphasize is by the time they get really high in the atmosphere and they've got so much little energy left, because they have been spreading that energy out as they've radiated it, they've got so little energy left that when they're striking surfaces, if I was to put a balloon up there for them to be striking the outside of, they are going to be creating an almost insignificant pressure. So when we look at that line between the top of the atmosphere and space, we aren't looking at a pressurized system. And again, we've looked at the difference between pressurized and pressure. We're not looking at a pressurized system. We're looking at matter that struggles to create any pressure when it touches the surface of anything at all. It's simply already spread out its energy as far as it can. I want to emphasize that we talked about gases not spreading out infinitely. The amount of volume a gas takes up depends on the temperature and the mass of that gas. So this whole idea that for some reason, just because there's gas up there, it's going to jump off and break that rule and spread out into space is just absolutely ridiculous. And I've not even talked about gravity yet. I've not even talked about the work that these particles have to do to overcome that force of gravity, etc., etc. What I hope I've done is put enough holes in this to get some sensible questions back. And maybe, if I get those sensible questions, I can turn this into a series of videos for those people who are really interested. This has been really a very beginner's guide with lots and lots and lots of things left out. But we'll see. My bet is that I'll get no serious questions at all. I'll get no serious discussion points. I'll get people talking about equations on whiteboards, and I'll get people talking about diagrams, and I'll get people popping balloons on a couch. Another thing that I'm sure will happen is people will keep talking about a pressurized container rather than a pressure gradient and where that pressure gradient ends. And this is a tired old argument that we know we're not going to get an answer to, but this is where it becomes dishonest for me. The people who feature in this video and more are massively intellectually dishonest. They won't address that. They will keep on talking about a tire pressure or pressure in a balloon or pressure in a canister. They will never ever factor into the question they're asking this sort of pressure gradient, because they just haven't got an answer to it. And this is what's making me really tired of having this sort of like discourse with people that believe the earth is flat, is they don't want to have that discourse. They don't want to take it further at all. So, you know, let's see what questions we get back from this. And I bet it won't be many. But if there are, like I said, I will expand on it, and I will continue to make more in-depth videos on this, which is beginner's guide, really.